Okay. So I'm very happy to be hosting Xizhi Han's talk today. So Xizhi got his BS from Peking University in 2016. And at the moment, he's now a PhD student in physics at Stanford University under Sean Hartnell. So he is a recipient of the Peking University Scholarship and the Stanford Graduate Fellowships Program in Science and Engineering. And today he's going to be talking about quantum many-body bootstrap. So please help me in welcoming either by muting yourselves or by clapping virtually, Xizhi Han.
Thank you for the invitation and the introduction. Today I hope to talk about my recent work on a numerical method for solving many-body quantum systems. The archive number is here, and you can see more about the details in that paper. Okay, let's get started. So first, I would like to talk a bit about the motivation behind this work. Of course, we know that quantum many-body systems are very important and interesting in all areas of physics. But there are already many different numerical methods for solving such systems. For example, the tensor network-based methods like the DMRG, MPS, or quantum Monte Carlo, or other variational methods that assumes some kind of structure of the quantum wave function. The problem itself is intrinsically difficult. We have some quantum computational complexity understanding of such problems. For example, finding the ground state energy for general lattice system is computationally hard. So it is not possible to come up with a perfect algorithm. By perfect, I mean it's efficient, accurate, and applicable to general lattice systems. Okay, so that's not possible. So there must be some trade-offs between the things that we want in a numerical algorithm. For the efficiency, so let's see. For example, the quantum Monte Carlo algorithms, they are not biased, but there might be some problems with fermions. So the variance of the samples will be large, so the result will have a large variance. So it's not biased, but there's a problem of efficiency. For the other usual variational methods, they're more efficient when there are some problems for quantum Monte Carlos, but we don't really know the bias we are making by assuming those variational wave functions. Sometimes it's hard to estimate how much error we made in making these assumptions. Also, most of the algorithms we have now, they have a complexity scaling with system size. So usually people do with a finite lattice on a torus, for example, and they can extrapolate results to infinite systems. So usually people are doing numerics on finite systems, and those finite systems also have a finite dimensional local Hilbert space, like the fermions, the spins. For bosonic systems, it is a little bit trickier because there's an infinite dimensional Hilbert space on each lattice size. Okay, so these are all different aspects of the numerics we're having now, and they emphasize different aspects of this efficiency, accuracy, and generality trade-off. Any questions about this? Okay, great. So I think I have an hour for this talk, right?
Yes, you did.
Okay, great. Okay, so now I want to propose a method that's kind of complementary in the three aspects, and I will first tell you what are the special things that are good for the method I'm going to propose. So it's called a bootstrapping method. So it basically constrains the operator expectation values in quantum many-body systems by some first principle algebraic equalities or inequalities. So the method I'm going to propose, it is algebraic. It means it only works with expectation values of strings of operators, but it doesn't care what kind of operators that they are. Okay, so they can be bosonic operators, they can be fermionic operators. The only difference is that when you commute the operators, there's some commutator or anti-commutators that appears, but it doesn't really care whether it has a locally finite Hilbert space or not. One good thing about this is that's also how we first you applied this kind of bootstrapping algorithm. We applied it first to certain matrix models. So those models have some significance in string theory. They're n by n matrices, and n can be arbitrarily large. So we're most interested in the limit where n is infinite. Then, for example, the conventional quantum Monte Carlo cannot deal with the infinite n, of course, because the complexity scales with the size of the matrices. But due to the algebraic nature of this bootstrap algorithm, we can do infinite n systems directly. Okay, so that's a good thing. That's a bit different than other numerics. The second thing about this method, I think the good thing is it's rigorous. So it always gives you rigorous bounds on ground state observables, for example. So there's no bias. There's always rigorous, and the size of the interval decreases when we have more computational power. So it always gives you rigorous bounds, and that may be good for answering some qualitative questions about the ground states. When we care more about some quantities are zero or not, rather than carrying precisely like the 10th digits of those quantities. That's the second thing. The third thing I think that's good is it's bootstrapping directly from first principles, like symmetries, positivity, and locality. So it's applicable for general quantum systems. We don't really need any a priori knowledge of such systems, and it works out of the box. So that's the second aspect. Any questions? Okay, great. Now the third question is, what are the looking forward? What are the applications that I think that are most interesting? The method first, it can give you lower bounds on ground state energy. The second thing is when it is combined with the upper bound of energy from variational methods, it gives lower and upper bounds on local observables. Also, all bounds converge to exact results when you have more computational power. So those are the promises of this algorithm, and I will talk about this soon. Okay, so this is an overview of how I think this method fits into a garden of many numerical methods we have now for quantum many-body systems. Yeah, feel free to interrupt me if you have any questions. So, okay, let's start with a simple example. Okay, I want to show you how the method works in the simplest example of anharmonic oscillator. So it's just a one-dimensional quantum mechanical problem where you have anharmonic potential. So how do we usually solve this? We write down the Schrodinger equation, we solve the differential equation, and we find the spectrum and the eigenstates of the Hamiltonian. Okay, so that's how we usually deal with this kind of systems. We solve differential equations. Now, instead of solving differential equations, the other thing that we can do is bootstrapping from what we know for sure, for certain about these systems. For example, I know that in an energy eigenstate, the expectation value of the commutator between the Hamiltonian and any other operator must be 0. That's just a first principle constraint because the state commutes with the Hamiltonian. This also works for thermal states, but in this talk, I will focus on, for example, the ground state or other energy eigenstate of the Hamiltonian. Then what can we learn from this simple looking constraint? The first thing is actually we can work out some of the observables just from these constraints, okay, without knowing anything, without solving any kind of differential equations. Let's take the operator O in its equation to be x squared. And it commutes with the potential, of course. So only the terms that remains comes from the commutator between the kinetic term and the x squared. So what we get is the xp expectation value is minus px expectation value. But at the same time, we know that we have a quantum commutation relation between x and p that tells us that we also know their difference in expectation values. So in the end, we know that exactly what their expectation values are just from this symmetry analysis, okay, without knowing anything about the potential or solving any equations. That's the simplest example, for example. The second example is the well-known virial theorem. In quantum mechanics, there's also a virial theorem in systems with a polynomial potential. To prove the virial theorem, one actually takes this operator O to be xp. So that's basically counting the degree, the dimension of the operator in the Hamiltonian. And in this case, P has dimension -1 and X has dimension +1. So in the end, we have this equality, okay, minus 2p squared plus 2x squared plus 4x to the fourth power is 0. So this equality links expectation values of the potential and the kinetic term. Okay, that's why it's called a virial theorem. So that's two very simple applications of this symmetry constraint, but we can already see that it is kind of powerful. Any questions? Okay, great. Now we want to do this more systematically. I just picked some random operators and write down some random equations. But of course, we can do this more systematically by choosing the operator O to be a power of X times a power of P. The first thing we know that it can always be reduced to the values of X to some power or X to some power times P. Because whenever you have P squared, you can get rid of that from this virial theorem, okay? From this Hamiltonian. Because this Hamiltonian, assuming that in an energy eigenstate, having this Hamiltonian times any operator must be energy times the same operator. And there, I can always trade P squared for X squared plus G X to the fourth power. So in the end, I can reduce any operator expectation values to X powers of X or with at most 1P in the operator. The next step is then take O to be powers of X. And this symmetry equation tells us that this expectation values with at most 1P can be reduced to all powers of X too. And the final step is there is also a recurrence relation between expectation values of X. So in the end, the upshot is any operator expectation value in the single particle example can be reduced to two real numbers. One of them is the expected value of x squared, and the other is the energy of the eigenstate that we are thinking about. Okay, so that's a very powerful statement, and it really only works in this single particle example. Yeah, let's see. With these equalities, okay, with the equalities from symmetries, we have now reduced the problem of finding the constraints for x squared and the energy. How do we find the constraint then? Now we come to the positivity constraint. That's why the method is called a bootstrapping method. Basically, the idea is simple, is that the positive operators, of course, have positive expectation values in quantum states. Now, this operator O can be chosen as a linear combination of some other operators. So the OI, I can choose the operator basis OI here, and I will call them the trial operators. If I expand this operator O in terms of these OIs, then the conclusion is that this matrix of operator expectation values must be positive semi-definite. Okay, that's from the fact that the expectation value of O dagger O must be positive. Okay, so now we actually have some kind of constraints for x squared and the energy as well. So in the single particle example, it really looks like this. Okay, so this 1 x squared, the powers of x, they are the operators OI that I choose in this positivity constraints. And now from the fact that this matrix must be positive semi-definite, I have a semi-definite constraint on operator expectation values like this. For example, in the upper left corner, this is the statement that the connected two-point function of x squared must be positive. So it's x4, the expectation value must be greater than x squared, expectation value squared. Similarly, you have a more elaborate constraint for other operator expectation values. And we know that all the operator expectation values can be reduced to x squared and the energy. So the algorithm is now, okay, you give me a pair of values. Sorry, my email just popped up for no reason. Let me see. Okay. Okay, good. Okay, sorry about that. So now the algorithm works as follows. You give me a pair of values, your guess, for the expected value of x squared and the energy. Then I can use the recurrence relation to work out all the operator expectation values, and I put them in this matrix. Then for some of the values you give me, this matrix won't be positive, of course. Then I know that your guess for x squared and the energy must be incorrect. Okay, so in this way, not all the values of x squared and energy are allowed. Only some of them are. And the allowed pairs of values get more and more limited when you have more constraints. So in a plot, this is what it looks like in this single particle example. So the shaded region is the values for the energy and the x squared that are allowed by the symmetry and the positivity constraints. This red cross is the exact value that I know from solving the Schrodinger equation. And this k is a maximal power of x that I consider in these trial operators. So more operators I consider, the larger k, the region gets smaller and smaller. And it's actually quite effective and powerful even for a moderate number of operators. You can see even if I only consider x to the power of 9, you already got a very small region, of course, which contains the exact answer. So that's the plot that I have in this paper, the bootstrapping matrix quantum mechanics. In this paper, we worked out this single particle example and had this plot in it. This is for the ground state. We also have an island for the first excited state. So here is island for the first excited state. So it is quite interesting to see that after applying these constraints, the allowed region of parameters actually split up into many islands. And there's an island near each point in the spectrum of the Hamiltonian. And the higher energy eigenstates need more constraints to be accurate. Before going on, any questions about this single particle example?
I see. Maybe it's a technical question. By the way, nice to see you here. My question is in the last page concerning your 5 times 5 matrix. How is the energy expectation value involved?
Yeah. So previously, for example, let's see. I have this visual theorem, which says that p squared is a combination of x squared and x to the 4th.
Okay.
Right. If I plug this into the Hamiltonian, then I can write the energy as some combination of x squared and x4.
Okay, I see.
Right. So that tells me where the energy is. The energy, this x to the power of 4 is actually a function of the energy and the x squared.
Okay, thanks.
That makes sense. Okay, great. Thank you. So this is the single particle example. The simplest example, it looks interesting, and it gives us another way of solving this kind of quantum mechanical problem.
I have a very quick question also, please. You say the way you do this is when you say that the commutator of H with O, and you take the expectation value is 0 for the symmetry, right? So can you say how many symmetries, for example, do you need to constrain all the possible operators?
Here, I only use this symmetry. The commutator with H is 0.
Yes. For this, is it necessary that O is a symmetry?
Of course, there are other symmetries. There are some other constraints from other symmetries. For example, there is a Z2 symmetry of this Hamiltonian, right? And that's why I got zeros in these entries. The odd powers of X are 0. And that's due to the Z2 symmetry. Of course, there can be other symmetries in different problems. Yeah, there can be other symmetries, but this is always true. It's not necessary to employ all the symmetries, although it will be more effective if you use more symmetries.
Right. For example, how about, okay, so this is, you need this to be some finite power of, let's say, x squared in this case, right? So what if you want something like e to the x squared or something like that?
Okay. So that's about what kind of operators you choose as this O, right? So if you have e to the power of x in this Hamiltonian, then of course, if you take the commutator, this O won't be a polynomial in x, for example.
Yes.
But for example, you can include those exponential operators as operators O2, and you can write equalities between them without expanding them like into powers of x.
Okay.
Then you still have some bootstrap equations between those operators. yeah, without writing them as polynomials. That's also doable.
Okay. Thanks.
Yeah, thanks.
Yeah, perhaps it's a very similar question, right? So Bootstrap programs are world famous in conformal field theory, right?
Yes.
Conformal field theory has a lot of symmetry, and my understanding was always that Bootstrap works because you have your full package of conformal operators, right? You have this whole structure of C-point OPs, etc. Perhaps you come to it, but perhaps it's already a moment in time to ask it. Where is the correspondence with the Bootstrap in CFT? I mean, you have something that may be very general.
Yeah, that's a good question. So the Bootstrap here, I think why I call it Bootstrap, because first, it only relies on first principles. It doesn't really needs more information about the system. And I think the essential point is this positivity constraints. That is related to the reflection positivity in the conformal Bootstrap. But of course, in conformal field theories, another very powerful thing is the conformal symmetry. But my point in this paper is actually both conformal symmetry and this positivity constraints, they are both very powerful and they are separate. Okay, so in general quantum many-body systems, we don't have those conformal symmetries, but with this positivity symmetries alone, they can already provide very constraining results. Okay, so my point is the conformal Bootstrap is of course very powerful and successful, but actually it doesn't, even without conformal symmetry, the positivity constraint itself is already very powerful.
Very interesting to you.
Thank you. Okay, let's go on. So this is a single particle example, and we will say, okay, I can solve the Schrodinger equation anyway. Why do I need this? The one point that we made in this bootstrapping matrix quantum mechanics paper is that you can solve the Schrodinger equation, of course, for this one particle example. But if you replace this one particle by larger matrices, by Hermitian matrices, then you have to solve many differential equations. That's a much more complicated problem. But the point is, from a bootstrapping point of view, there isn't actually much difference, because the bootstrapping only concerns operators like powers of x, powers of p, and for matrices, it's the same. The operators are still trace of powers of x and p. And so the bootstrap method is algebraic, and it's directly applicable for large n systems. That's why that's one good thing about this method. The complexity doesn't really scale with the number of degrees of freedom like this in these larger matrices. And the results are very good as well. In those matrix models, even only considering short strings of matrices, we can already get bootstrap constraints that are very close to exact results. These plots are in this bootstrapping matrix quantum mechanics paper. And yeah, I just want to show you that it has advantage for larger systems, and it's also very powerful there. The idea is very similar to the single particle example. Okay, but for this audience, it might be more interested in like lattice systems, like the Hubbard model. And this bootstrapping method is applicable to Hubbard models too. So it's a lattice of fermions with this hopping term and this on-site Hubbard interaction. In one dimension, the Hubbard model is solvable, and we know the exact results. I will use that to benchmark the method. In 2 dimensions, at half filling, the other numerics, they give consistent results, so I can benchmark with them there too. But for intermediate interaction and intermediate filling, those approximate methods, they don't always give you consistent results. Okay, so sometimes the difference is beyond the numerical uncertainty. Okay, so in that case, I hope that this method could provide some complementary information to other numerics. So for Hubbard models, the algorithm works in pretty much the same way. But as previously a question mentioned, we have more symmetries in Hubbard models. Besides the time translation symmetry generated by the Hamiltonian, we also have spin rotation symmetries, lattice translation and rotation symmetries, charge conservation, etc. And for all those conserved charges, I can put in an equality between expectation values from taking commutator with the conserved quantity. Okay, now we have many more symmetries. The second problem is, of course, the first constraints only give you equalities, and I need some inequalities from the positivity constraints. And it's the same. It's that this matrix of operator inner products must be positive semi-definite. But the problem now is, what should I choose as this basis of trial operators? Previously, I was choosing the operators like the powers of x and powers of p. Now, this lattice system has a geometric locality. It's an infinite lattice. By the way, I always work with infinite lattices. And now I can only choose a finite number of operators to put into this matrix constraint. So the question is then, which operators do I choose in this positivity constraint? My idea is maybe we should choose operators that are local, because it seems that locality should play a role in the energy of these lattice systems. So for a monomial of fermion operators, I define a locality degree, which is basically the sum of the L1 norm of their lattice vectors of this fermion creation or annihilation operators. So I've assumed that there's origin somewhere in the lattice, and I only choose a product of fermion operators that are close to that specific lattice site.
Quick question.
Yes.
Okay, we did a very quick question. If you try this out instead in momentum space?
Yes, we can do in momentum space as well. That's right.
And then I guess the claim is that real space works better than momentum space. Or is it?
So in momentum space, we still need some truncations, right? And we need some sums. So for example, there can be CK1, CK2, CK3, and we need to choose, we cannot choose all the Ks. There must be some combinations of the Ks that we can choose. And in the end, it's actually equivalent to some real space smearing. So I would say that, yes, we can also choose operators that are local in K space. But in practice, I don't see much difference between the two choices. Does that answer your question?
Yes, it does.
More quantitatively, the operators that I choose in this bootstrapping constraints are operators with locality degree less than k. So this integer number k limits the operators I choose for these constraints, and the larger the k is, the more operators that I'm using. That's the idea. The performance of this method is really controlled by this only one parameter k. That is how many operators I choose for the constraints. At a higher level, let's see, at a higher level, what I'm doing is I have constraints from symmetries and positivity that looks like this. So this V is a vector of operator expectation values where this OI is a basis of operators. Now I have some linear constraints between them from the symmetries. Also, I have that a matrix of expectation values must be positive semi-definite. Now, given these two constraints, not all the energies are allowed. We've already seen that in the single particle example. With these constraints, the allowed energy, they split into islands. Okay, there is a set of allowed energy. Not all energies are allowed. Now, what's the minimal energy that is allowed by both constraints? The problem is then a semi-definite programming problem. It's a convex problem. It's minimizing a linear combination of expectation values subject to two constraints. Because this problem is semi-definite, so it can be solved in polynomial time on a classical computer. And this gives us a lower bound on energy. That's quite different from variational method, which usually gives us upper bound. This one gives us lower bound. Okay, why is this a lower bound? Well, I think it's more intuitive to draw a picture. Let's say this red interval is the region of energies that are consistent with the constraints. Of course, the real energy must be consistent with all the constraints, so it must be within this interval of allowed energies. And now, if I minimize the energy in this allowed region, it must be a lower bound of the true energy. Is that clear? So the special thing is that I got the lower bound instead of upper bound on ground state energy, and that is complementary to the variational method. Any questions about this point? Okay, great. Now I have a lower bound. I can ask how close it is to the exact result. In the one-dimensional Hubbard model, we know the exact answer, which is this E naught. These are the exact answer from Beth and Sons. And the Bootstrap method also gives some lower bounds on energy. Here it is bigger than this because there's a minus sign. We see that they're actually quite close for this one-dimensional Hubbard model at all couplings. It's like within 1% accuracy.
Sorry, can you explain the parameters here?
Oh, this n is the filling factor for the Hubbard model. So it's the number of fermions per site, per lattice site. This U is the Hubbard interaction, which is the repulsive interaction, on-site repulsive interaction between spin up and spin down fermions.
Okay, thanks.
This K basically limits the number of operators that I use in the constraints. Yeah, this D is so-called the double occupancy. It's only one when there are two fermions on one side. So that's one of the notations. We see that both for the energy and the observables will get close to like 1% accuracy to the exact results in this one-dimensional model. So it really works. At least in principle, it works. Now we can ask, okay, so this is one dimension. We know the exact results. What about 2 dimensions? Well, in 2 dimensions, you can imagine that there are many more operators because the lattice is now 2-dimensional. But still we get a bound that's close, somewhat close, like within 5% accuracy to the numerical results from other methods. So it is, in this sense, it is competitive with the other numerical methods. And I think the accuracy can be improved if we have more computational powers. For now, we are doing it on my laptop, like in 2 hours for each point. So probably we can push it to larger K on a cluster. But this is more like a proof. Yes, any question?
To the best of my knowledge, MG and DMAT give upper bounds, right, for the energy. So this is basically the window between the lower bound and the upper bound. Is that the way to?
Yes, combined with this DMAT, we have an interval of the exact interval of ground state energy for the Hubbard model in 2 dimensions. Yes.
That's the first, right?
Sorry, what was
That's the first. I have not seen that before, that anybody can estimate where it is. There are no lower bounds, as you argued. Everything is variational in one or the other sense.
Yes, but there are also some other works on lower bounds in quantum mechanics systems. But for the Hubbard model, in the thermodynamic limit, I think this is the first.
Yeah, I haven't seen it. Yeah. Interesting.
Thank you for the comments. So we really have a small interval. The good thing about this, as I said in the motivation section, we really have a rigorous control of the ground state energy and from this bootstrap method. And it's not perfect, but it's actually quite tight. Okay, so similarly, you can do it for a wave from half filling. So this is for the energy. I will talk about observable bounds later, but for now, at least, we have a bound for ground state energy. I will talk, maybe I will talk this briefly. So the thing I want to talk here is, I want to give you some analytically arguments that this method converges to the correct answer. So the bound really becomes infinitely tight when you have an infinite number of operators. So the basic idea is, now we think about the limit where we have infinite computational power. So we can impose an infinite number of constraints, and let's see if that picks out the correct expectation value of operators. And my claim is that it indeed gives you a unique solution from this operator constraints, and it's just a simple exercise in basically in linear algebra. So these are the constraints. So this map F from operators to numbers is basically evaluating the expectation value of operators. The constraint we had before are the symmetry, positivity, and some Hermitian. I didn't mention this, but of course it's also true. The expectation value of O dagger is the expectation value of O complex conjugated. Also, the identity have the expectation value 1. Okay, so these are somewhat trivial constraints. Then from these constraints, we can show that this map F must be the correct expectation value in the ground state of the Hamiltonian, if I impose the constraints for arbitrary operator O. So this is an analytic argument that at least in principle, when we have an infinite number of constraints, the bounds converges to the exact results. But even if we don't have an infinite number of computational resources, we always get a valid bound on ground state energies.
And a question. So the number of constraints is talking to conserved quantities, right? And
yes.
When you have a quantum chaotic system, right, and there are so few conserved quantities that symmetry doesn't really protect you from delocalizing all the Hilbert space, right? Become quantum chaotic. And now I get confused, because when I go to a random matrix-like system, right, now conservation laws, then I have 5 fewer constraints. And how can it still be that I get the right answer, right? That it apparently does not matter how dense your constraint density is, so to say.
Yeah, so yes, so look at, so in this argument, I'm only imposing one constraint from symmetry. That is, it is energy eigenstate. So it's the time translation invariance. That's true in any energy eigenstate. I'm not really imposing any constraints from other conserved charges. The point is,
so it's basically like you need only this little set of constraints that's on your view graph,
yes,
in order to be sure that you are converging.
yes.
And that's very general. Any system will basically satisfy this.
Yes.
In any matrix system, you can figure out operators that do all of this.
Yes.
So
My claim is for this argument to work, I only need one constraint from symmetry, that's time translation invariance. But of course, in practice, I only have a finite number of operators. So more conserved charges you know, the more effective the algorithm will be. But that's not necessary. You can, it suffices if you only impose this constraint.
Okay, thanks.
Okay, great. That was an analytic argument. Numerically, I can also show you how the error, by the error, I mean the tightness of the bound, the difference between the lower bound and the exact answer decreases as I increase the number of operators in the constraint. So this dimension C1 is the number of operators in my operator basis for the constraints. And this is a log-log basis, a log-log axis. So it seems that in this numeric experiment, for the one-dimensional Hubbard model, the energy error, not actually the error, the energy difference decreases polynomially in computational time or in the number of operators. So of course we know that there's some complexity statement that for arbitrary lattice systems, it cannot just decrease polynomially, but it seems that at least for one-dimensional Hubbard model and the two-dimensional Hubbard models, they decrease polynomially. So that's a good sign. It's not like exponentially expensive to get to higher accuracies. But even without very high accuracy, we can already get some interesting bounds on ground state properties.
But wait, we know, right, that you're dealing with a signful two-dimensional Hubbard model. That's lots of fermion signs, blah blah. I think the issue may well be right, that to reach the real ground state may take exponentially long time, but to get an estimate for a lower bound of an expectation value may still be polynomial. Right, so the bottom line is when you further delocalize in the very, very big hill space, you gain increasingly less energy. So energy is not really a very good measure of, you know, how well your ground state wave function is made when you're interested in very, very long range entanglement.
Yes, yes. Yeah, I agree with what you said.
Yeah, makes sense, right?
Yeah, makes sense. But it's also true that even a bound on ground state energy, an accurate bound on ground state energy is computationally hard. That is also true.
But wait, an upper bound, right, a variational business, is always the same thing that you make an exponentially expensive problem into a polynomial problem. Right? Be hard.
Yeah, right. That's true.
Yeah, right. Yeah, I think it's comparable. It's okay.
Yeah, thank you for the comments. So that's about the ground state energy lower bound and its convergence. The next problem is how can we bound other observables? So now we have a lower bound on ground state energy. We can also get upper bound from variational methods. So we have a lower and upper bound on energy. From that, we can impose another constraint that the energy must be less than this upper bound. Of course, it's greater than the lower bound. Then we can get rigorous bounds on observables too by imposing this extra constraint and then minimizing or maximizing operator expectation value. So let's see. In the two-dimensional Hubbard model, I can do this for the ground state upper occupancy, and I get lower and upper bounds. This is the first line is lower bound. The second line is upper bound, and we see that the result from DMET or DMRG, they lie nicely in this interval. So this interval is less tight than ground state energy, but it's still a non-trivial bound. Another interesting application may be that we can use this to bound ground state ordering. I also did that for magnetization into the Hubbard model. I can get an upper bound, but of course there's always a ground state that doesn't break the rotational symmetry. So the lower bound for magnetization is always 0, but I can get an upper bound. Okay, so that's what I have now. I have a lower bound on energy. I can get rigorous bounds on other ground state observables. I can bound ground state ordering. I can have an upper bound on ground state ordering. The lower bound is more difficult because for now it's always 0 because there's always a symmetric ground state.
Yet another, it's just interesting. Right, so there is the famous procedure to figure out spontaneous symmetry breaking, right? And it's about order of limits, right? So you add an explicit symmetry breaking field to the Hamiltonian, right? And you keep that finite, take the thermodynamic limit, and then you let that field go to 0, right? And you get your full size magnetization. When you reverse the limits, you find your exact constant. Can't you add a small symmetry breaking field to it? Because you expect that it eventually saturates, and then by making this, the field smaller, you can extrapolate to the limit.
Yes, yeah. So yeah, that's a
very small field has a very big effect on the magnetization. That is the big deal there, right? So even when you let your field go to 0 in the thermodynamic limit, you still have your full size order parameter.
Yes, yeah. So yeah, the one thing I can do, of course, is I can, let me see if I can draw on this. I can.
It just suggests, I don't think you tried it, but
yeah.
Lower bound.
That's a good comment. That's also something that we are thinking about.
I wish you.
Yeah, let me see if I can draw this. This looks weird, but okay. So this horizontal axis can be the symmetry breaking external field that I turn on, and this the vertical axis is the energy. So I can get a region of allowed energies like this from the bootstrapping. So I do have a bound because for example, the magnetization is just the derivative of energy at 0. But because this bound is not, there's a finite range of possible values for E, so I don't really have a bound on its derivative.
But you should try my suggestion because that should work. That should give you a lower bound, right? It's just this counterintuitive fact that a very tiny external symmetry breaking field suffices to make a very large response in the form of an order parameter. That's just a bit enhanced, right, compared to what would be a 0 field when the field is not 0.
Yeah.
It's sort of switch of the order parameter in the ground state that you can catch, I think.
Yes, yeah, yes. We indeed got an upper bound, but we didn't get a lower bound. But that's.
In this way, you can get a lower bound. I'm pretty sure.
Yeah.
That it will work.
Yeah, we'll try that. Thank you for the comment. Okay, so that's what I plan to talk about today, and we can discuss more, of course. So basically, the new things that I think about this method, it gives you rigorous bounds on ground state energies and the expectation values. The good thing about the method is algebraic. It really works for large N systems too. It only needs input from first principles, so we don't really need any knowledge for the Hamiltonian system, and it is mathematically rigorous. The optimization problem is convex, so there's a mathematical guarantee for its accuracy and complexity. For future work, the thing that we are trying to do now is, as I just we just discussed Lagrange ordering, of course, in Hubbard model. That's very interesting. Also, we can generalize the method to bilocal operators. For now, the operator basis I choose include only operators that are local near some site in the lattice. But we can do bilocal operators, possibly, so we can extrapolate correlation lengths or something like that. Also, it should be possible to do Green's functions at finite frequency and wave factors. Of course, those are still bounds on Green's functions. And those are all interesting directions. Another interesting direction is, for now, the method only bootstrapping from first principles, but sometimes we know some other knowledge about the system. For example, it's a BCS condensate. Then how to combine that knowledge with this bootstrapping method, it's also an interesting question that we are thinking about. Yeah, I'm happy to discuss more if you have any questions or comments. Thanks.
Okay, so if anybody has any questions, you can either raise your hand or you can just unmute yourself. Yes. Yeah.
Hi, thanks for the really nice talk. I have a question about your definition of locality. You wrote some definition for locality L, right?
Yes.
Yeah. Yes. So from this, it doesn't look like you're like really constrained to point operators, right? Like if it was like some small loop operator, you could still like allow it if K was like sufficiently like large. So I was wondering like if you could like implement this for say a Wilson loop operator in like a gauge theory sort of a context.
Yes.
Any thought of that?
Yeah, actually, those QCD, those lattice gauge theories, people also did some bootstrapping. So essentially bootstrapping things on those lattice systems. So that's definitely possible. But there is the same problems is still there. It's about this locality. So you can only bootstrapping small Wilson loops, not very large ones. But that's doable.
I see. Okay, thanks.
I have another question. So you say this locality is a problem for operators. For example, Green's functions, if they're bilocal and they're far away, could it perhaps be that if you consider operators local in momentum space, that might be resolving the issue?
Yes, yeah, that's actually what I meant by local operators. It's yeah, we're going to consider more about the momentum picture of this, but it's still in progress.
So any other questions? So I had one question. It might be somewhat naive, but what about beyond, say, a lattice model?
Yeah, we apply this method to matrix models. Too,
Okay. Okay.
Of course, a single particle example, quantum mechanics example, this infinite n matrix models, the lattice models. So the upshot is like any model that's quantum mechanical with locality, with some kind of locality. So in matrix model, this is like more like the K locality. It's not really spatial locality. It's about the length of the operators. So yeah, it's generally applicable to many different systems.
Okay. Okay. Any other questions? So maybe I'll wait 5 seconds in case anybody wants to unmute themselves. Okay, so let's thank Xizhi again.
Yeah, thank you very much. Thanks.